Hello there, my name is Anand Rajamani, and today I'll be talking about command-based programming. This video is the second in the Programming Your Robot series, and we'll be making a simple command-based robot program and drive a motor. Now before I start explaining command-based programming, I'm going to preface this by saying that WPIlib has an already great little page on what is command-based programming and how does it work. So if you have any doubts about what I'm saying here, or you want to learn more about command-based programming, make sure you refer back to the docs here. It's all under this FRC Java programming part of it, under FRC control system. And it goes over all kinds of things to do with command-based programming right here. So it's a great way to learn more about command-based programming. Now, with that said, I'm going to go ahead and re-explain what command-based programming is in a slightly different manner. So, command-based programming is made up of two things. We've got commands and we've got subsystems. So, commands, subsystems. And subsystems might be something like, let's say we have drivetrain, arm, and elevator. 3 subsystems in my robot. Might also have like pneumatic stuff or like intakes or whatever, right? But this is like so of these subsystems. And my commands would be something like drive to position. Actually, I'm going to color code these. So I'd say drive to position. Drive with joystick. Arm to position. Elevator manual. So I might have manual elevator control there. And basically, subsystems contain methods inside of them. So drivetrain might have a position method in it that moves the robot to a position, right? That should be position int p or something, right? Like your target position. And then it might have a drive method that takes in like a double left, double right, that runs the left and right sides of the drivetrain at different speeds. And the arm's going to have similar, like maybe another position method, and the elevator is going to have a move method, things like that. So what commands do is they're going to call the methods in subsystems. So for example, drive to position is going to call something in the drivetrain subsystem, and so is drive with joystick. And arm position is going to do the same thing. It's going to call inside the arm subsystem. And elevator manual is going to call methods from the elevator subsystem. And each command is going to require subsystems that it uses. So elevator manual only uses the elevator subsystem, so it's going to require the elevator. And the drive commands will require the drivetrain. So if another command is called when a different command is like currently running that requires the same subsystem, then the newer command is just going to overwrite the old one and kick it out. So this prevents you from having clashes where you have multiple parts of your code trying to access the same thing at the same time and messing with it. So that can be very useful. And how do we determine what command to run when? Well, that's going to be the OI subsystems job, or the OI classes job, not subsystem. This is a class. So the OI class is going to contain things like the joysticks, joystick axes, right? So like if a gamepad has like a couple joystick axes on it, and then buttons. And what OI is going to do is going to say, okay, when the A button is pressed, drive to position, so I'm going to put like an A here. And then run, oops, there you go. And then run drive with joystick just the rest of the time, so it's going to be like the default thing. Let's say like def, so that's not in, that's going to be defined in my subsystem that this is the default command. And then if I press A, it'll drive to position. R to position is going to be like if I press the Y button. An elevator manual, or should really color code this, Y. And then elevator manual is going to be like, well, it's called maybe a default command for elevator that just takes the joysticks and then uses those. So like this. And so the way this is going to work is, OI, when a button is pressed, is going to say, okay, well, let's make a command, and the command's going to run, and it's going to finish. And then that manages the commands. It's called the scheduler. Here's our scheduler. And the scheduler is really where all the magic happens, because the scheduler is going to determine what commands get run and when. So, for example, if I press the Y button, the scheduler is going to run arm to position. Okay, so if I press the Y button, arm to position gets added to the scheduler. That's what it's called added to the scheduler. And the scheduler is going to run this command, or a part of this command, every 20 milliseconds. So I'm going to say, okay, every 20 milliseconds I want to tell the motor controller, move to this position. So it keeps on doing that. And once it gets to the position, then it'll exit out. So the scheduler will kick the command. It'll just remove it. And so it will no longer be run. Same thing, elevator manual is going to get called pretty much all the time because the default command, and then it will kick out whenever another command interrupts it. Something like drive with joystick is going to be called all the time, and then somebody presses the A button, and then the A button is going to kick this guy out, so it's gone, and then the drive to position command is going to be added in its place once the A button is pressed. And once we've gotten to the position, or we quit out for some other reason, this guy goes away, and then we're back to driving with the joystick. So, to summarize, commands call methods that are in subsystems, and they require subsystems. And you can have multiple commands that correspond to a single subsystem. And the OI is going to call commands based on button presses. And the scheduler is going to take these commands that OI has called, it's going to run them, and when the commands finish, it'll eject them. Before we get started, make sure you have the Phoenix Toolsuite as well as all the development tools installed. Follow the instructions on the Getting Started page of the WPIlib screenstepslive to ensure that your robot is running normally. I'm going to walk through replicating my basic robot project. The GitHub repository is linked in the description. Follow along in code, or just trace my actions on the finished project. So first, let's start by making a template-based, command-based robot project. So I'm going to come here to the top right to the little WPIlib icon, click on it, and I want to do a new project. So I'm going to do proj, and there it is, create a new project. And it'll give me my little project creator wizard, pretty nice. So I'm going to want a template, because I'm going to start with the command-based robot template, not like a full working example. Language, I'm going to want to do Java. And of course, command robot. Select folder to place the project into. Okay, so I'll select a new project folder. I have my GitHub and video 2. Select. Enter a project name. Video 2 robot. Sure. And my team number is 1072, so I'm going to pick the same. And there it is, generate project. Would you like to open the folder? Yes, current window. Here we go. And so here's my robot project. It's going to build now that the first time it's running. There it is, build successful in 21 seconds. Great. So the first thing I want to do here is come over to this SRC and find Robot.java. This is going to be the container that holds all of our robot stuff. That means subsystems, that means figuring out what runs when, that sort of thing. So Robot.java is pretty important, and we'll come back here and we'll update it as we go through making this project. So you can see here there's several methods here. So robot.init is going to be called when the robot is first started up, meaning when it's powered on, and also after you deploy code. So any kind of like setup or configurations will only be done one time. Like if you're calculating your wheel diameter or something, you can do that in init, and it won't take up extra time later in your program. Robot periodic, it says right here, function called every robot packet and the mode every 20 milliseconds. And this says periodic is by default 20 milliseconds. I think you can change that by going into one of the settings, but we'll ignore that for now. 20 milliseconds is fine. So this is disabled init. So when we disable the robot, still periodic while the robot's disabled. And you notice here that we have this scheduler.getInstance.run line in a few places. Right there, autonomous periodic and teleop periodic. And that's basically just going to say run all of the commands that are in the schedule. Like I explained before, you put the commands in the scheduler, and the scheduler will run the commands until they're done and then kick them out. So this will make sure that we run our scheduler during our autonomous, teleop, and disabled periodic. In the interest of saving some time, I'm actually just going to copy over all of my Robot.java code, and I'm going to explain it from the GitHub project that's linked in the description. And the reason for that is that it takes a long time to actually type things out in code, and it's pretty boring. So instead, I'll just copy over what I have, and then I'll explain what the lines do. So come over to a new window real quick. Select all, paste it in, and save that. And there's going to be some errors here, you'll notice. And basically all I've done is I just deleted a lot of comments, mostly to keep this thing shorter. And I'm making a new subsystem called TestMotors here, so I'm instantiating that. And I'm making my OI, which is going to be my joysticks and that sort of thing. And I'm going to add a couple prints here so I know that my code is running. You'll notice here we're getting errors because I never actually made a subsystem for that. So first, I'm going to delete these example command and example subsystem they've given us. And I'm going to make a thing called TestMotors exactly as I'm going to copy paste this. So I'm going to go to subsystems, right click, create a new class / command, and I want to make a subsystem. Just paste that in there, TestMotors, and hit enter. Now you'll notice they give us, when we make a new subsystem, some very, very basic skeleton of what we're supposed to be doing. So there's a init default command. This is going to define a command that gets run whenever no other command is using the subsystem at the moment. So for example, I might have something that holds my arm in place here. So like an arm stay in place command whenever I'm not trying to move it somewhere else. And it just extends subsystem as you do. So again, I'm going to go and copy all of the code from the GitHub here. So I just copied it from a new window, select all, paste, save this, and we have some errors here. A lot of errors actually. And this is because you'll notice all of these are my cross-the-road electronic stuff. The com.ctre stuff just isn't showing up. That's because I haven't actually included my vendor libraries yet. So before we try and explain what this code does, why don't we clear out some of the errors. So I'm going to go over here to the command palette, and I'm going to type in vendor, and hit manage vendor libraries. And I'm going to want to install new libraries offline. Now make sure that you follow the instructions in screenstepslive to get your Phoenix library and stuff downloaded. So I'm going to do install new libraries offline. There it is, CTRA Phoenix should automatically show up. Hit check, hit OK, and yeah, sure, let's run a build. So I'm getting less stuff. There you go, everything else is pretty much working here. My RobotMap.TestMotors isn't in there yet, and neither is my drive the % command, but let's ignore that for now. So first, I'm going to come over here to my Talon SRX Victor SPX. So this is going to declare a Talon, so a Talon SRX motor controller, and I'm going to call it Master Talon. And I have a Victor SPX called Slave Victor. I also have a Boolean called isCloseLooping. We don't need that right now, so I'm just going to delete it. And I'm just going to run this controller init method in TestMotors. I'm going to replace this with a better thing later, but for now, I'm going to individually initialize all of my configurations. So when I make my TestMotors class, so basically in robot init, I'm going to run a controller init. And controller init's going to, make a new instance of Talon and Victor. And these are going to be their CAN IDs. You want to make sure that all of your Talons have different CAN IDs and all of your Victors have different CAN IDs. You can have, however, like a Victor of CAN ID 1 and a Talon of CAN ID 1. You can do like 1 and 1. That's totally valid. You just can't have multiple of the same device with the same CAN ID. That's all. I'm going to first run a config factory default here. That's going to set all of my configurations to the default. So if I change something later in the code and I forget to change it back, so for example, I add a limit switch and then I don't remove the limit switch, next time I boot on the robot, sometimes the Talon will keep settings like that. And I want to make sure that it doesn't have any settings. It'll be completely fresh when I first boot it on. So I'm going to run a config factory default right here. There's also a timeout. If a CAN command fails to send like the first time, then it'll keep on trying to send it until some number of milliseconds pass. So in this case, I believe this is like usually like 10 milliseconds or something. So I might do like 10. And so it'll keep on trying to send it for 10 milliseconds before giving up. And it's typically good practice to have a timeout just in case there's any kind of error. I set my neutral mode. So on a brake mode versus coast mode. There's coast, there's brake. There's merits to both. And we'll talk more about it when we actually start moving our motors around. But suffice to say that brake mode will slow your robot down faster than coast mode will. I'm going to run my set inverted. So if my wheels are spinning the wrong way, I want to invert the output. So that positive output corresponds to the robot moving forward. So that's going to be my set inverted there. And this might be a true or a false. Who knows? True if you want to invert it, false if you don't. And I'm going to set my slave to follow my master. And I'm also going to invert the slave's output again to make sure that my stuff is all spinning the same direction. Okay, very, very frequently people forget to do their set inverteds, and then they're like, why is my robot locking up? Well, it's because your motors are trying to fight each other when they're trying to go forward. And so making sure your inversion stuff is correct is important. Now, finally, we've got this drive method. It's the only method in here that actually does anything. So it's going to take in two things, a master output and a slave output. And just for now, actually, I'm just going to comment out the follow. And I'm going to do a slave victor dot set. Copy all this. A percent output. So I send a thing from -1 to 1, and a 1 is 100%, -1 is -100%, so full forward versus full backwards. And I'm just going to tell them to each go at different outputs based on my arguments here. And finally, in a default command, like I said before, it's the command that runs when nothing else is using the subsystem. So I'm just going to do a drive with % command that's going to be run all the time whenever I'm not doing something else. Now, there's a couple things we need to do. First, we need to update robot map, and then we also need to make a command. So I'm going to do the command first, and then we'll go back and add in this robot map stuff. So let's save this. And to make a new command, same as subsystem, just right-click on commands, go to create new class command. You want a command. And we want to call this drive with %, same as this guy down here. There it is, my drive with %.java. And now see that, no more error. Very nice. Once again, I'm going to come over to a different window, copy all of my drive with % stuff, and just paste that into here. And for now, I'm going to just remove some, like a scaling line here, because we don't need that right now. So I'm going to get the most basic thing working. So drive with % is just going to drive our motors based on a joystick. Very straightforward. So in a command, like this is a skeleton here. In a command, you have several methods you can use. So first is my constructor. I'm going to run a requires robot.TestMotors thing. And TestMotors is going to be an instance of my TestMotors subsystem in robot. And I want to make sure I do this that way in case another command tries to require the same subsystem, the scheduler was going to kick this guy out and then let the new one take its place. Very important to do that. In initialize, you initialize any kind of like settings or anything you need to do. In my case, I can just use all the default settings from the Talon that we put in right here, the controller in it. So that's all the same. So nothing going to initialize. Execute is going to get called every 20 milliseconds, every time the scheduler is run, which is every 20 milliseconds. I'm setting my throttle here to be equal to my the left y-axis or the left joystick's y-axis on my controller, and my turn is going to be get left x. And there's also this dead zone thing. This is just, I'll go over this more later when we write the dead zone method, but it's basically going to be a method that just kicks out the inputs if they're like less than 0.2 or something on a scale of -1 to 1. And that's because I don't want a problem where the joystick just doesn't return to center to kill me. And you'll see this more if you try it yourself. If you don't dead zone your joysticks, then when they're near the center of the travel, sometimes they'll be at like 5 or 10%, and then you'll just start moving randomly, and it's very annoying. So it's always important to dead zone these things. Then I'm just going to call the drive method, which again we have in TestMotors right here. Pass in my throttle plus turn and throttle minus turn. So this way I turn based on my x-axis, because plus and minus, and I go forward using my y-axis, throttle and throttle. Is finished, so the scheduler is going to check is finished after the command is run. And if the command is already finished, it'll return true. That's it. In my case, I'm just going to return true immediately, so it'll quit out of the command immediately. So it sets the throttle, and then it quits out. That's all. You can also do return false, because this is a default command. I could do return false, and then when I call another command, it'll kick this out automatically. But in this case, return true is fine. It runs this once, and then it just quits out. End is just like, if I want to say like done driving or something, .out.print line done driving. Can do that. However, in this case, because it's being run every 20 milliseconds and it's finishing immediately, I don't necessarily need this line here. It's just going to print a bunch of times. It's going to print once every 20 milliseconds. Interrupted is, well, when another command, right there, when another command requires one or more of the same subsystem scheduled to run. So if something else tries to get this out, like I'm trying to run a drive to position command, then this will get called. And usually in interrupted, I'll just call end. But sometimes you'll want to do something special if it's interrupted. like maybe get rid of some settings that you put in. All right, and we got two more to do. We got to do OI and we got to do RobotMap. So let's do OI first. We'll finish up the RobotMap. So let's do OI first. The OI default they give you isn't very good. It doesn't really explain as much as I'd like, and it doesn't include everything correctly. I had to go online to find what other people use for their OI, and it can be fairly complicated. But in our case, we're going to start with something simple. So again, I'm going to copy over all of my code from another place. Yoink. There's another command here that I'm just not going to use right now, because we don't need it. It's just like a zeroing sensors command that we're not going to use yet. Now, first of all, make sure you include all the stuff. So you want to include your joystick button and joystick button stuff. Pretty straightforward. Otherwise, you can't use joysticks. Here's dead zone. Dead zone. This is going to define the minimum threshold level of the throttle before it even recognizes throttle. So here's my dead zone method we were talking about before. Taking some input from usually -1 to 1. So input from -1 to 1, usually. If dead zone is greater than the absolute value of the input, so if my input's like 0.1 or -0.1, this is true, then it'll just return 0. So it'll be no output. However, if it's greater than a magnitude of 0.2, it'll return the input. That's all. So it just stops you from having problems where you release the joystick and then it doesn't quite return to center. In my case, my joystick's really bad, so it's about 0.2. Most joysticks will be closer to around 0.1 or less. Now back up to here. I define a joystick. A joystick is any kind of gamepad, and this 0 here comes from the driver station, which I'll show when we get to the driver station. But basically, it's like the order. You can set the order of your controllers, and this is the 0th controller. I define a button on the joystick, so I have button A, which is the A button on my Xbox controller. It's going to be button number 1. Button B is going to be button number 2. X and Y are going to be 3 and 4. I don't know what 5 through 8 are. I haven't mapped them yet, so I'm just leaving them as button 5, button 6, so on and so forth. And these are just going to define buttons that we can bind commands to. So that line that I deleted earlier, that's going to be a command. Let me copy that over actually real quick. So this one will zero the sensors when button Y is pressed. So there's one pressed, and there's also some other types of things. Oopsies, button Y dot. Cancel when pressed, toggle when pressed, when pressed. There's a whole lot of things you can do. Toggle when active, when released. So you can bind your commands to the buttons in whatever way makes sense. And right here, get left Y and get left X. Just gonna get my sticks here. So it'll get the throttle axis and the turn axis, and then it'll multiply it by the inversion. In my case, my y-axis is actually inverted, so pushing up on the stick makes it go negative. So this is gonna be equal to -1 to invert whatever I get from the axis. The x is normal. The x is left is negative, right is positive. All right, so last thing we got to do now is fill out my robot map. So robot map can be used for a lot of things. The default one they give you tells you mapping from the ports and sensors and actuators wired to a variable name. So if you have 2 robots, or you just you unplug parts of your robot and want to plug them back in, robot map is a way you can just map all your ports to something. So you don't have to have magic numbers floating on your code. I like to put most of my magic numbers in robot map because I just don't like having them around. Even putting this dead zone thing in OI, which is where it makes sense, right, bugs me a little bit. I prefer to have everything in robot map. So I'm going to copy stuff from robot map in the window right here. Paste that in. And so in this case, I have the timeout that's on it. So I have a 25 millisecond timeout. That's actually pretty high. I'm going to set that to 10 milliseconds. And I'm also going to have another little subclass in here called TestMotors, same name as this, but not the same class. That's just going to define all the constants for the TestMotors class. Putting invert y and invert left x in here is pretty bad. Those should really be in OI, but I'm going to put them in roadmap for now, just so I don't have to modify too much code. And invert master, invert slave, my speed scale, that was in there before, but I deleted it, so I'm going to delete this. So here are my CAN IDs here. So if we go back to TestMotors, this should be this CAN ID. And that's just because if I change anything, if I change out a motor control or something, I want to be able to just refer to one class to figure out where everything went. So that's going to be RobotMap.TestMotors.masterDrive. There it is. Right here. That's like there. Okay. There you go. These are going to be equal to 1 because set my candidate to 1. Got my y-axis, x-axis, my inversions. Like I said, the y is inverted, the x is not. And everything else is pretty much the same. Okay, we're almost done. I still have an error in OI, so for now I'm just going to comment out this command. We'll add it back later. But right now I have code that should drive my robot. So let's go back to robot and we can review this. So we make our test motor subsystem. Test motors is like what I call my testing board of motors. So I have 2 motor controllers on my testing board, so I call this test motors. In your case, it might be called drivetrain or something, based on what it is. What is you trying to control, that is. In OI, I get my X and Y joystick stuff. In the test motor subsystem, I have a default command, so whenever nothing's being run with the test motor subsystem, then I'm going to run a drive with % command. Drive with % takes that OI stuff, the OI, Y, and X, dead zones them, and then drives with them. Okay, so pretty straightforward. Well, maybe not straightforward, but it should work. This is like the most basic command-based robot thing that you can do. So to upload this, or to deploy this, make sure you're connected to your robot's radio, and then hit Shift F5, and if we pray, it'll compile correctly the first time. There it is! Okay, so now we should have deployed the code to the robot. So why don't I go ahead and open up the Driverstation, and we can see what happens when I'm driving the robot. Okay, so I've got Driverstation up now, and let's quickly run through all the Driverstation tabs here. So right here you select the mode you want to do. So to operative mode is driver control, autonomous is autonomous control, practice and test. Practice will run a full practice match for you basically, and test is just runs whatever's in this test periodic here. There's some stat stuff here. You can set your team number, make sure it's set correctly, timing for the match. Like I said, this is the controller thing I was talking about earlier, so you can move controllers around. These visual devices are kind of like virtual controllers that I have on my computer right now. And so if I go to this controller here, if I push up on the stick, you'll notice that y-axis decreases. And also notice that doesn't quite return to center on its own. So like that right there is releasing the stick. Notice how that axis is just below where it should be. Now, I've also got I don't know what this is called actually, power and can, sure. This basically tells you if there's any shorts or faults anywhere. So if you see a lot of comms faults, that's a bad thing. CAN bus utilization is like how much of the CAN bus am I using. So you're allowed to transmit 1 megabit per second over the CAN bus. And so 12% means we're transmitting about 120 kilobit per second. That's good. Typically, if your utilization's over like 80% or so, things can have problems. You want to make sure that all of these are also 0. Bus off is like a disconnect. TX full is like where the buffer's completely full. That's often goes hand in hand with utilization, things of that nature. For the most part, just look at utilization, make sure you're not super duper omega high, and you'll be fine. This one tells you, if you have joystick plugged in, robot code and communications, and your battery voltage. All right, so we're just about ready to start running this thing. So I'm going to move back to teleoperated mode here. I'm going to go over here so we can see our controller stuff, and I'm going to enable the robot. There it is. It's enabled. I'm getting an overrun message. That basically means that the loop took longer than 20 milliseconds to run. Sometimes it'll happen at the first loop or something, so it's not a big deal. Just make sure it doesn't happen like frequently or you have problems. Come back to here. Okay. Let's go ahead and push up on the stick. There it is. That's a spin. You can see that the lights are going green when I'm going forward, and when I go backwards, they go red. Pretty straightforward there. And we can look at some analytics actually over the Phoenix Tuner. So why don't I go ahead and open that up too. Phoenix Tuner is included with your install of all the Phoenix Toolsuite library stuff. So to use it, basically you put in the IP address of your guy there, or if you got it over USB over this IP here. To do that, you can view your CAN devices and you can do things with those. First of all, this tab here, so I can click on my Talon, can update my firmware. Make sure that you are updating your firmware before you use any new motor controllers or anything. You also can update all your Talons and all your Victors if you need to. And the firmware is also downloaded with all the Phoenix Toolsuite. Okay. You can change the ID. My ID is already correct. I put ID 1 for everything. Go over here to control, and if I have my robot enabled here, then I can enable the control and I can set my motors like that. And you can also configure, I can also configure whatever I want. There's a lot of configurations here. We'll go over most of these in subsequent videos. You can run a self-test, and you can plot the output of the thing. So, for example, I threw a little hub onto my gearbox so I can see the rotation a bit better on the screen. So I'm going to enable teleop here, and then I'm going to enable my plot. And there's my plot, and I'm going to plot my, first I'm just going to output my output percent, okay? So when I go forward, you'll see output goes up, and when I release the stick, goes down. And you can see the command here on the left, right? Very, very useful here. We go left and right, and you can, it's right, there you go, it moves. Actually come back here as well. Now, I can plot other things. For example, I can plot my position. So, let's not do outputs, do position. There's my position increasing when I go forward, and my position decreasing when I go backward. There it is. You can also plot your velocity and your closed loop error if you're keeping track of that. And you see whenever I release the stick, it comes back to 0. Very, very handy. So I use Phoenix Tuner a lot whenever I'm debugging or trying to set up a closed loop control thing, and we'll do that more in later videos as well. That's it for this video. The next video will cover closed loop control and PID. Thanks for watching, and see you soon.